He was the head of fuel economy, performance, and powertrain synthesis at Chrysler. And prior to that, he spent well over 25 years in the engine and powertrain systems and development. Who would have ever thought that I would have gone ahead and chose one of the parts being a powertrain part, and we've got an expert amongst us here. So, great.
All right, thank you. There's aerospace people here. How many own a car?
Almost everybody, right?
Okay, all right, good. So maybe this will be relevant.
Yeah. Just a sec. Nick's moving the, advancing the thing.
Yeah.
So no safety things here, but we'll start with a statement, $200 billion. That's what the regulations for fuel economy are going to cost. Ultimately, you, the consumer, because it'll get passed on to you between now and 2025. And that's just in the US, so you spread that through all the other countries that have regulations, and there's going to literally be trillions of dollars spent on improving the efficiency of the automobile over the next 10 years. It is an important issue. There's a lot of issues associated with improving the efficiency of automobile beyond greenhouse gas, but certainly energy independence for certain countries, including ours, is a noble goal. So you want your system to be very efficient, because if you're going to spend $200 billion, you want to get the most out of it. So if you went to the morning session, a couple of these slides are repeats in here. I had a last-minute request to join a morning session, and I had already created this, so I recycled a little bit. This is a graph of years versus fuel economy in the light-duty automotive space. You can see the tremendous rise. Passenger car requirements in blue there. Red is the truck requirements. So by 2025, we're going out to 40 mile per gallon trucks. Those are pickup truck type vehicles. 50 plus mile per gallon passenger cars on average. This is a fleet average. Not every car will get that. Some will be less, some will be more. And then the dots there are the performance to those vehicles up to about 2013. So you can see passenger cars are a little overachieving. Trucks are a little underachieving. They'll have to catch up. I like to put this, since we're talking about propulsion and energy, I like to put this in an efficiency domain. Perhaps from the turbine systems, those numbers will look familiar to you, but the efficiencies of the light-duty automotive are not great. Operating on the regulated drive cycles, they're about 20%. They need to go up to about 30% thermal efficiency or overall cycle efficiency by the 2025. So that's a 50% increase in efficiency. So if you're in the power systems area, that's a gigantic leap, I would say. In your career, have you done 50% in 40 years? Not likely. You end up 50% in 10 years is a gigantic goal. Hence the $200 billion price tag. And this becomes an important systems engineering, again, because you want to get your $200 billion to put to good use. This is what the automotive companies are doing right now in response to those regulations. I'm looking at the US here. And really, if you look back, I'm starting this graph in 1996. Most of the technologies, if you follow the auto industry at all, or you at least follow the commercials, you've heard some of these, direct injection, turbocharging, 7 and 8 speed transmissions, stop-start. Those were non-existent 10 years ago. So what's happening with the automotive systems beyond the electrical stuff that we talked about earlier is the powertrains are becoming very complex, very diverse. It used to be, when I started my career, everything was gasoline, naturally aspirated, 4-speed transmissions. Now the auto industry is all over the board. You have to have control systems for every one of those different iterations. And in some cars, there's multiple iterations. You look at a Ford Fusion, you have a DI turbo, you have a hybrid, you have a naturally aspirated, you have a battery electric. All in one car. The control system, basic control system, has to cover all that complexity. So that is driving quite a challenge within the auto industry. So just to take a quick look at systems challenges, really revolving around fuel economy, because that's what I wanted to talk about here with the energy side of it. We talk about the powertrain. Most people think about the engine, or what we call the power source. but it really also encompasses the transmission, the driveline, parasitics, like you have to cool the engine, power control system, energy recovery, kinetic energy recovery on hybrids or heat energy that's coming, exhaust emissions control. That's a very large and costly element of your car. In fact, people are cutting your catalysts out of your car if you leave them out because the precious metal in the catalyst is so expensive. Evaporative systems and energy storage. That's what we call the powertrain in the automotive space. But when you want to get fuel efficiency out of this powertrain, you have to consider all of these elements of the powertrain, not just the power source or the engine. Now, I'll give you an example at the end of the discussion where we believe an OEM focus only on the power source and not the other parameters of the powertrain. Now, when you want to get good fuel economy, you have to think about the other elements that make up fuel economy. There's the parts of the car that aren't in the powertrain, the aerodynamics, the brake drag, the tire rolling resistance. The driver, how you drive your car, is going to significantly affect where you drive your car, which is the drive cycle. Do you drive on the highway? Do you drive in the city? Do you start your car for 30 seconds and shut it off every day? How do you drive it? It's going to have a big impact. So we have to consider all of those when we look at the total energy demand function on an automobile. And then we talked about, I think it was very good in the beginning, you had your nodes. I have my nodes too. Basically, all of these interact. If I change the weight of the vehicle, that's going to change the way the transmission operates. If I change the aerodynamic drag of the vehicle, that's going to change how the engine operates. So you have to consider all of the interactions of the system to consider how you're going to achieve these fuel consumption and CO2 goals going forward. Now, when we get back to just the powertrain, most people think the powertrain is just there to deliver power and do it efficiently, and that is true. That's the items on the left there. But there's some mission-critical items that the powertrain's required. Safety. As I brought up Toyota earlier, that's controlled by the powertrain. That electronic throttle control, if you have a recent vintage car, your car is very likely electronic throttle control. Durability and reliability, thermal torque, things like that. Criteria pollutants, we're also regulated. Hydrocarbons, NOx, CO. The powertrain controls, and powertrain has to take care of that. Onboard diagnostics, check engine light if you've ever gotten one. That's what's happening there. That your control system in your vehicle is constantly monitoring hundreds of systems. And if it falls out of spec, you get a check engine light. We talked earlier about safety systems, or the gentleman asked about how do you test it. Sometimes as a customer, unfortunately, you're the test device. We don't want to get false on check engine lights, but they're just the nature of the business sometimes. The auto industry is getting much, much better at that. Drivability, how well does the car feel when it drives and accelerates? Noise, and then control system limits. And that's a very real issue within the auto industry is these are highly, highly complex systems, but I need to bring them down into a control system that's affordable, that we can put software on, that we can actually write the software to control it. So you end up with control systems that don't have the opportunity to deliver the ideal control. So all of these issues affect the performance of the powertrain, which then affects the performance of the fuel consumption, which then gets back to the whole $200 billion price tag I put up front. If I can't get past these, or these are degrading my performance enough, then I might have to consider other technologies. Okay? So I'm going to give you an example, and then I'll end here, of a technology that's quite popular right now. You see a lot of advertisements of downsized direct injection turbo. There's several manufacturers out there that do this. And within the industry, and I should say, and I don't want to pick on academics, but mainly in the research and the academic environment, it's touted as 8 to 10%. And researchers at all of the OEMs, if you talk to them, they'll probably give you that number. We've looked at hundreds of vehicles, and we've never seen that number. And the reason is, we believe, the system integration was not done properly. So unless you're in the power generating device, this plot may not mean much to you. But on the x-axis is how highly loaded the powertrain is, and the x-axis is fuel consumption. So the concept of downsized DI turbo here is that I shrink the engine, which I push it at a higher operating point, which makes it more efficient, and almost every mechanical element is like that. Turbines, transmissions, gears, load them higher, they're more efficient. Engines are the same. Now, if I've made the engine smaller, it's less powerful, you're not going to enjoy it, so they put a turbo on it to bring the power back. These concepts are sold this way, and this is an isolated view of just the engine.
Just the part.
Just the part. So this is actually sold this way on the company. I'm not going to tell you who it is, but this is how it was sold. The team went to the management and said, look, we're going to get, and that green was 12, 13%. And then they did the full system integration. And we actually took, because it's public information, all of their certification data and decomposed it to find out what they really got. And so what I have here on the left is the larger displacement engine they started. I have the y-axis is fuel consumption. Okay, so higher is worse. You want to go lower fuel consumption. And we just walked across the items and decomposed their data to see what happened. And we saw that if the green bar goes down, it means they got a benefit from that area. And the first bar is idle fuel, meaning yes, they consumed less idle fuel. And the next one is coasting and braking. Yes, they reduced the fuel consumption on coasting and braking. And then that big 0.26 there is the graph I was showing you earlier where they gained the efficiency benefit by operating at a higher specific load, but then they gave it all back, or almost all of it back. So up to the point of the big green bar, we would agree with their early assessment. You're getting about 13% improvement in fuel efficiency, but you lost almost all of it because you did not consider the system. In this case, they had to lower the compression ratio of the engine. They had to add a high-pressure pump to be synergistic with the turbo. They did not consider certain thermal losses. And then they had to gear the car differently to get the same performance feel that was satisfying to the customer. All that gave back nearly the entire benefit. Now, these systems cost about $800. That's the manufacturer cost. That's not your cost. So $800, they went in, they might have sold it as a 12 to 13% improvement at $800. The management said, that's pretty good. When you're in the auto industry today and you're spending $100 or less per percent of improvement, we're taking it. It may not sound like a good deal, but that's a great deal today in the auto industry. Well, now you just made that thing $300 per percent. It's no longer a good deal. So the failure here was up front, they did not consider the entire system. They considered the part. By the way, to retool an engine, a high volume engine, redo the plant, change all the tooling, you're looking at about $1.5 billion. So in our view, that was $1.5 billion mistake. Now, how did they recover? They're attempting to recover. They're doing things to the car to help recover it so you as the customer still get the benefit, but it cost them and it set them back. So some takeaways here from our perspective of the auto industry. First of all, cost effectiveness is key because you as customers don't want to pay the price of getting to the 30% if we just put on some high-tech technology that's going to cost a lot. These cost-effective solutions really are the way for customer acceptance because we could today add a lot of technology to a car, achieve the 55 miles per gallon, but nobody would buy it because it's too expensive. Technology strategies early on in the phase when you're going, this maybe perhaps gets to the architecture question, it must be evaluated looking at it from a fully integrated system, not a part. So don't look at the performance of the part, consider basically the failure modes and effects, or integration failure modes and effects of what could happen to that strategy downstream there. And don't evaluate these technologies in what we call an isolated or controlled environment. In that case, it's in a very clean test facility running at a very specific operating condition under very specific conditions. That is not how you drive your car, and the system should not have been evaluated in that mode. Manufacturers and suppliers and researchers need, certainly in the auto industry, to spend more time, I believe, on integration focus rather than just technology focus. There's a lot of technology buzzwords in the auto industry. There's not a lot of integration buzzwords in the auto industry. And then regulators really need to understand these interactions, because when regulations are made on other parts of the vehicle, it challenges the interaction effect of the spider web I showed earlier, has some negative, sometimes negative consequences to the results. Oh.
Thank you, Greg. There we go. You know, the fuel efficiency number was a system behavior number, and people got lost and simply thought that a part would get you all the way there. Remember what a system is. A system is built from parts that interact together in a specific way to achieve an objective or a behavior, where no one part can do it by itself. It's a really good example. I was in the NRO as well, Paul, and I was in the system analysis staff branch they had there. I was worrying about a part that I thought made a $10 or $15 million difference. And my career mentor at the time took the equivalent of a baseball bat and went, wham, your job is to worry about $200 million issues, not $4 or $5 million issues. And his point at that time, actually her point at that time, was don't you get lost on the diesel engine in this element, when if you don't get the rest of these things balanced properly, you're going to cost me more than I can ever imagine. Good career advice, powerful career acceleration and thinking about it in a systems point of view. Another wonderful conversation is going to come here from Don Burns. Don is the head of Innovative Systems Engineering at Rolls-Royce Corporation, right here in Indianapolis, Indiana. He's held positions as Chief of Dynamics, Engineering Director of Transmissions and Structures, Engineering Director of Combustion, Engineering Director of Propulsion and Power Systems, and as I had said, is presently the head of Innovative Systems Engineering. Don?
Okay, thank you. I may change things up a little bit here. As my title says, I'm focused on innovation systems engineering. And what I'm going to describe today is what I think is the role of human element in innovating and getting that innovation to a product.
Let me see. I think he's busy changing. There we go.
Okay.
Yep.
The human element reminds me of a quote by Carl Sagan that said, "Avoidable human misery is more often caused not by stupidity, but by ignorance, and in particular, ignorance of ourselves." And I think one of the things to try and improve how we deliver system engineering is a better understanding of the differences of those who are on the team or in the team, and differences in the mindset and thought patterns of the various partners that might be in the endeavor. I want to start with organizational purpose. Our company, our purpose is to add high value and hopefully to receive some benefit from doing that as a company. This is a quote from Sir John Rose in 2009, but it talks about what is involved in high-value activity, and it's deep knowledge. And as things become more and more complex, that deep knowledge gets even deeper. And all of these characteristics, I'm not going to go through each one of them, are call out and require people with great depth in each one of those. But to really deliver that high value, you've got to integrate that depth. People with depth have a certain mindset. They're very focused, often blinded by their depth. And so integration requires getting them into the group and getting them more acclimated to deliver that. I think in COSI, in the Vision 2020, started to recognize that there is human limits. As we get more complex, there are human limits on comprehension, there are human limits on control of complex systems. And I think this is a good example of knowing ourselves and being able to recognize this. As I think about bringing innovation forward in a company, as it's more complex, it's harder to get people to see the significance of that technology and what it can mean to the product. And often the roles of people who are in management or in control can stifle the new technologies that are coming forward. So this is a very real problem, I think, as we try to shorten the innovation time. I'd like to start with a generic S-curve, and I'm going to spend most of my time on this. You have value on the y-axis, and then you have time and maturity and investment on the x-axis. And it's a typical S-curve where you start out with multiple ideas that need to be assessed quickly, and then you move up and try and take those ideas that winnow out and may more quickly get them into a development and into a first product. And then up towards the top, you try to introduce that into a product for the business. And up there at the top, you're really concerned about minimizing risk. And down at the bottom, you're concerned about searching for opportunities. And in between, you're trying to balance risk and opportunity. I want to mitigate the risk, but I don't want to lose the opportunity. In each one of those areas, there are multiple teams, and often in business today, there are global teams, there are university partners, there are government partners in trying to develop this technology. So there are a multiple number of people with different mindsets and perspectives on what we're trying to accomplish. So one thing that I think we need to recognize that each one of these areas, the strategic research area, the development area, the NPI area, all have their organization, their culture, their enabling parts of the business, and that these are different for each one of them. And also, there are different skills and different mindsets of the people and the leadership in each one of those three areas. Maybe to bring this out and make it more real, I would call these people down here at the first part of the curve explorers. They're trying to discover what is that next opportunity? What could I do? And that's their focus. The people in the development area are pioneers. They want to take the ground that's been captured by the explorers, and they want to start developing it. They want to make those ideas a reality. And then you have the settlers who are trying to perfect and optimize that reality and make it to the benefit of all. So, sorry about that. Go back. So it's important to recognize that there are gaps that occur between each of these areas that tend to slow down innovation. The handoff from the explorers to the pioneers tends to have a gap. From the pioneers to the settlers tends to have a gap because of the differences in mindset. So what's really needed here is a system integration, a mindset that looks at the whole picture and can mitigate those gaps between these different mindsets to increase the pace and the efficiency and effectivity of innovation. One way to do that, and I think in the 2025 vision of NCOSE, is to look at broadening the role of future system engineers, giving them a broader mindset that allows them to manage across this S-curve. That mindset has to have more of a social training in it, if you will, because you've got to deal with those people and get them to understand one another. And there has to be a development of tools to manage this human element, I think, going forward. The training is going to be very important to integrating these concepts into system engineering and the management of the human element in system engineering. Effective system engineering integration is going to require recognizing that human element and in progressing innovation going forward. And so I would close with some key points. Effective system integration requires looking at the whole S-curve and looking at the human element. It requires a matching maturity level and technical leaders in each of those areas. You need to focus on matching leaders with a maturity level of technology, and you may need to bring some settlers down into the pioneers, some of the explorers up into the pioneers, and cross-fertilize to get the handoff to be improved. You need to match processes and tools for each of those areas. And finally, need to keep stakeholders engaged and guide expectations based on that maturity journey. Now, this might seem simple, but it's not. It's not simple in the sense that, again, you're dealing with the human element. But what I wanted to bring it forward for was an awareness of why it's so difficult to innovate. No one in this chain of innovation development has a desire to hold up innovation, but it's the different mindsets that need to be integrated and the different behaviors that need to be integrated to speed up the pace of innovation. That's it.
Well, thank you, Don. I'd like to introduce John Wade. John, again, is a professor in the School of Systems and Engineering and Enterprises at Stevens Institute of Technology, and he serves as the Chief Technology Officer for the Systems Engineering Research Center. Previously, Dr. Wade was the Executive Vice President of Engineering at International Game Technology. You'll have to take him aside. He's got some wonderful stories.
I bet.
Where he managed corporate-wide research and development. And he is batting cleanup for us. John?
Thank you. Amazing. We've got, what, 20 odd people? I think there's more people now than when we started, so
Yeah.
thanks for that attention. So talking about the energy marketplace, sort of thinking about where we've been traditionally with energy and where we're going. And on the left, I've got the Coca-Cola machine, which sort of represents, the consumers of electricity. It's always there. There's a huge, vast network or infrastructure that makes sure that that Coca-Cola is in that machine, and it's cold for you when you want it. But that's basically the way the world looks. As we're moving forward and people now have the opportunity to generate their own power, to actually take their car, put it in the grid, plug it in, and actually use that as a means to store energy, we're changing the picture dramatically. It isn't a Coca-Cola that you buy, but actually it's more like an open bazaar, where people are going to be producing electricity, putting electricity on the grid. It's a distributed type of application. And we have a situation that moves from something that's complicated to something that's complex. You know, one of the questions in the earlier part of the session is how do you deal with that kind of complexity? And I think that's where we are with respect to systems, is we're moving from systems, you know, that are very complicated, but we're moving into a realm where systems are quite complex as well. I mean, if you look at systems, you know, traditionally mechanical, electrical types of systems were the beginning systems we had earlier last century, moving to electronic with isolated islands of software to software-intensive systems to network-intensive systems, and then moving on to enterprise systems of systems and you know, vastly larger systems. If you look at the automobile industry, what's remarkable to me is how far they've come and how quickly they have to go, because we're talking about automated automobiles. You know, what is that going to look like? I mean, that's a whole different world than we've seen in the past. So moving from something that was, you know, 20, 30 years ago electromechanical to something that's software intensive to something that's going to be part of a larger ecosystem is a huge change for us to make in a fairly short period of time. And as we sort of move up this chain, we've increased the complexity, the ambiguity, there's less control, there's more uncertainty, and the question is how are we going to address these challenges moving forward? If you look at the classic V, you know, the systems engineering V, the challenge with V is, first off, it just takes too long to get to the place where you actually validate the system. Does the system actually do what we want it to do? And it's too late quite often. Having developed computers, we brought in marketing, and then they had to create features out of all the defects, you know, that we created as engineers. And the better marketing people could make it sound better than it actually was. But the challenges that we had often in engineering were not that we didn't do a good job engineering, but we didn't understand how the system was actually going to be used. So for example, the marketing folks said, make sure the system never goes down. So the engineering developed all these means by which the system would never go down. But as it turns out, in our case, it meant that the service personnel had to go through this very complicated sort of recovery plan. And if they did anything wrong, they were going to get corrupted data. And if you're a service person and the system goes down, they yell at you. And if you corrupt data, they fire you. And so in essence, we were asking them to risk their careers each time they tried to use this capability, and they never used it because we never validated it. We never checked end-to-end at the beginning of the program. So you sort of see the V disappearing. You need to do the validation. You need to do the verification up front, and you need to do it continuously. It isn't something that you've done, you check it off, because the world changes, technology changes, your product changes. It changes as it's being developed because people are changing the way they design, decisions are made, and that sort of thing. And so we need to move to the place where we do continuous coherent development, where we're leveraging the computation, visualization, communication, information, and such, so that we're doing these activities all the time. And I have seen some companies be very successful with continuous V&V, but it requires three things in every company I've seen. It requires a commitment, because these sorts of things take years to develop. It isn't something that's going to give you payoff immediately. You have to be willing to go to root cause. Whenever you see something fail, you have to understand why did it fail, rather than just say, well, it's a bad test. And then the last thing you have to do is you have to automate. Unless you're willing to do all three of those things, you're not going to get to the place where you can do continuous V&V. But I think it's an essential capability if you want to keep up with technology and the way these systems are being used. Has anyone heard of Conway's Law? Mm-hmm. We've got one. I believe this so powerfully that any organization that designs a system will inevitably produce a design whose structure is a copy of the organization's communication structure. I totally believe that. You know, I've seen a software organization that had 2 compiler groups, and guess what? They had 2 compilers. You know, it just always works that way. The last company I was at, when I was at IGT, first we focused on what's our vision, what's our strategy, then what's our architecture. And I think all the panelists have discussed the critical importance of architecture. Once we had the architecture in place, then I invited all the management into the room, and I said, here's the architecture. Do we understand the architecture? We went through yes. Then I put up the org chart, which was exactly the same thing. And I said, do we understand that? Now, the thing about it was the first level managers were gleeful because they understood what they were doing. The directors were a little uneasy, and the VPs were ripped because these fiefdoms that they'd accumulated over 20 years were now being taken away from them, in place of something that made, a lot more sense in terms of the way the architecture played out. But I can tell you that when we did the development, the product looked like the architecture. And I've done it the other way around, where it tried to make it look like the architecture, and it eventually looks like the organization no matter what you do. So when you're doing your integration, you are going to see your organization. And if your organization has a supply chain that's disaggregated and it's not aligned along interfaces, that's what you're going to find. So there's no surprises and no shocks when you're doing integration, because it's going to look like your organization. So take your organization, draw the critical interfaces in your system, superimpose it, and where they don't line up, you're going to have huge numbers of failures. Looking at sort of systems, and this is a really interesting framework. I encourage you to sort of look it up, review it. But it sort of talks about known systems, which are sort of simpler systems, knowable systems, which are complicated systems, complex systems, and then chaotic types of systems. A lot of the systems that we've been talking about, I believe, are complicated systems. They're complicated because there's so many parts, but the behavior's fairly predictable. Now, one of the challenges with these is that cause and effect could be separated over time and space, but they're predictable. I mean, they're analytic. You can use analysis. You can use reductionism on these types of systems. And the approach you usually take is sort of a sense, analyze, and respond. As we move from the Coca-Cola to the bazaar, we're moving into complex systems. And these systems are quite different. Cause and effect are only coherent in retrospect, and they do not repeat. So if you were to take that system and move it in time and let it play out again, it might play out to be very different than the way it played out in the past. And so when you have those types of systems, really the best you can do is, as we talked earlier, is to put in instrumentation, probe those systems, and try to see how those systems are behaved, sense those systems, and then respond to those. If you look here, if you're starting in the system space where you're looking at complicated systems and you want to move to a complex system, explore. Don't just jump whole hog and say, okay, we're going to try this new system. It's going to have all these complex capabilities. Try a few, explore. Understand that if they don't work, you can sort of fall back. Sometimes people will work in the complex space and they want to sort of nail things down and make it more predictable. And in that case, you really have to sort of move back here and use some of the templates that you have in this space. But when we're talking about moving systems forward, I believe we're going to be moving most of the systems we have from this complicated knowable place into this complex space. So we have to embrace complexity, and I think that means that moving from the belief that we can understand how a system works deterministically to how a system behaves probabilistically. My generation, you buy a new OS, you actually would buy a book and pull it out and try to understand how it works. Forget about it. The approach, I believe, where you just try to see how it behaves is going to be much more effective, because the system's changing continuously with time. Again, if it's a complex system, every day is different than the past days, so you can never keep up with it if you're trying to deterministically understand how it's going to play out. You have to look in terms of how that system behaves. So what can you do? First, I think you need to instrument and you need to monitor the system. If you don't understand the system that you have, how can you possibly understand the system that you want to create? As we mentioned, I think everyone mentioned, most of the systems we create are brownfield systems. Oh, for the glory of greenfield systems, which is funny because in academia we tend to just teach greenfield and we don't teach brownfield at all. And what they're going to find are brownfield systems. But it's really important to understand what the critical parts of the system are and what do you actually want to instrument and what do you actually want to monitor. There's a great skill in that. I think systems thinking is all about that, which is what's the critical aspects of the system that are really the important ones. Because we can bury ourselves with data, and we probably have, with the capabilities to instrument. But those who are insightful and really know what to measure, those are the people that are going to move the organization and system understanding forward. We need to model and we need to simulate. Now, I don't believe we need to model and simulate everything. I think we need to model and simulate the things that are most critical. And again, I think that's a place where you have to understand what are the most important parts of the system. And I think that you need to take your model in your simulation and you need to validate it with what's actually happening in the field. And I think that process of validation of what's actually happening in the existing system, along with what could be happening in the future system is critical to us as well. I don't think you can get by with one or the other. And unfortunately, we talk about model-based systems engineering a lot, but we haven't talked a lot about instrumented and measured systems engineering as well. And then I think we need to apply some big data analytics to all the information that we've collected. For example, there are folks, I believe at Carnegie Mellon, who look at software engineers' behaviors, and based on who's checking in and who's checking out, you run some analytics. You can get a good sense if somebody's touching this, what are the ripple effects that are going to happen within that system. If you collect information in terms of the systems that you have in the field, you can get a really good sense of predicting when systems are going to fail. One of the things we noticed in computer systems was just measuring the power current, the surges and such around some of these mainframe-like devices allowed us to predict when those systems were going to fail, not even understanding what was happening in the systems itself. We also need to characterize the tipping points in the system. Again, if you look at your laptop, it's a simple case. We understand power, we understand temperature, voltage, frequency. We understand where the tipping points are, where it's safe to operate, and where it's not safe to operate. For these types of complex systems, we need to understand the places that are safe operation and the places that are not safe, and make sure that if it gets to a place where we're not confident, we take corrective action. So for example, if you look at the financial system, you look at trading that's happening. When things go too far astray, they'll shut trading down on Wall Street. I mean, because they know that they're in a place where anything could happen, and they'd rather just shut the system down and let things cool off than trying to proceed forward. Your systems could be made much simpler if you're willing to step in and say, we're not going to guarantee operation in this space, and if it starts to get into this space, we're going to pull back. I think when you look at the automobile industry, it's the only way that you could get to that place, because trying to engineer your way through all those spaces, virtually impossible. And I think you need to have sort of active engagement with the system to maintain it overall timescales. It isn't to say that you've got somebody or some number of people who understand the system backwards, forwards through all time, but you have some people who are the immediate response team. They understand what happens in the short term. And you've got another group of people who understand what happens in the medium term, and another group that may understand what happens in the long term, because the types of behaviors you have are very different in each of those different cases. And the skill sets of the engineers and the analysts are very different in those spaces as well. So I don't think you can just have the emergency response team, but you need to have a response team that's able to respond in very different epochs of time. So we need to experiment, we need to evolve as we get into this space. John Gall, from a book called Systematics, it's great. You can Google it, you can look at it on Wikipedia, if you will. But he has a number of statements. He's made a number of statements. One, a complex system cannot be made to work. It either works or it doesn't. A simple system designed from scratch sometimes works. Some complex systems actually work. A complex system that works is invariably found to have evolved from a simple system that works. There are very few complex systems that are created from scratch that just work. I mean, if you look at the complicated or the complex systems that we have today, like the internet, it wasn't created as the internet. It was a much simpler type of networking capability that evolved over time. And most of the complex systems we see are systems that have evolved over time. So I think the notion that we can engineer a complex system from scratch and believe that it's going to be successful is probably fairly erroneous. Last thing I'd like to say, and it's been mentioned at least once, there's a book here, a magazine, A World in Motion, Systems Engineering Vision 2025. It talks about a lot of the things that we've discussed as a panel today. It's available on the INCOSE website. It's 30 megabytes, so you're probably not going to email it to a lot of people. But please download, give it a read, and give feedback, to INCOSE and to the authorship. I think it's a good document, a good place to move forward.
We'll have
Excellent.
In case you didn't hear, John Yuhas said that look for the INCOSI desk, which is up on the next level here, right kind of kitty corner from registration, and they'll have a few copies there. Well, thank you, John. Well, I think we're down past the 7th inning stretch to about the 9th inning here.
Thanks.
I want to
Good ideas there.
to emphasize that in one way or another, what you have heard is a sharing that says, you know, for those who can maintain a systems perspective and have curiosity, being able to discern what's a part versus a system, okay? And stay focused on where the big impacts come from. And very often the really big impacts come from not the part itself, but the interaction of the parts not achieving this higher behavior. Quite frankly, it's been good for all of these panel members' careers and perspectives. With that, I want to let you know that I'm going to be asking for questions again, and as I give you a chance to think about it, I want to kind of start with Dave Wong with a question that I would like each one of the panel members to share a little perspective on. David and colleagues, you know, no matter where we are in an organization, it seems that we can always look up and there's still somebody up there, right, in an organizational sense. When I was a senior at Booz Allen, I said, you don't, and I was mentoring someone, I said, I don't think you realize, no matter where you are in an organization, you're still a schmuck. You know?
Good to remember that, yeah.
Yep. And so as you watch leadership around your organization and they're dealing with a complex issue, what integration problem do you most often see them overlooking as part of their overall solution? So again, the idea is, as leaders are dealing with complex day-to-day problems, what integration issue is most commonly overlooked in your viewpoint? David?
I see a split, and it depends upon the characteristics and the background and the training of the person I'm looking upwards to. If they are a technical individual, if they come out of an engineering organization, et cetera, then their background, technology and training, et cetera, makes them more comfortable with components, parts, physical things. And what they will tend to therefore overlook is the psychology, the human in the system, okay? I can then flip it exactly the other way. If I'm looking upward to a business individual, someone who's made their living in dealing with social systems, they will often underestimate the physical aspects, the technology aspects, and in particular, they'll expect deterministic behavior out of physical aspects or software aspects where that won't exist. So those two kind of manifest themselves in that way.
Thank you, David. Greg, do you have a perspective on this?
I think it's related. It's really where the person has been from. They tend to lean on or leverage that experience and bias that experience in their decision making. And then it leads to a more pillarized view of that. So I think just trying to stay away, remembering your past, but also constantly pushing on the edges.
Thank you. Don?
Yeah, I agree with David. I think that, that people who have the engineering background understand the technical side and of complexity and integrating it. It does come down to the human element and making sure we have the right skill sets, the right people in place to execute. And that's difficult. I think that there is, as Nkosi has pointed out, a growing awareness of that gap, and I think that there is a growing change within our organization to recognize that.
Well, thank you. Eric, what perspective do you have to share?
You know, I would say that the concept of understanding at what level do you want to optimize, because whatever level's chosen to optimize, you will sub-optimize the other levels. And understanding whether you want to optimize at the subsystem, you want to optimize at the system, or optimize at the component level, depending on what you want to sell, what your customers want to buy, and how do you bring value to your customers. Complex topic that, and really critical to just setting the business strategy as well as the architecture for any system.
Mm-hmm. Mm-hmm. Paul?
Well, I would agree, as several have mentioned, that this interface between the technology and the people is kind of a big issue. I guess the one thing I would add that's maybe a little different than some have said is that when you're designing a system, you know, you're balancing lots of things and lots of requirements, and ultimately you can't have everything. So you have to understand how you're going to make those trades. You know, are you going to sacrifice some performance for security? Are you willing to trade usability for something else? Or how much, you know, lots of times in specs we'll just say something like the system needs to be secure and maintainable. But you have to really explore what that means to be able to make the right trades in your ultimate system design, and sometimes we don't do that so well.
Okay. John?
Quite often, the simple things. You go, you know, how could that? How many people saw the movie Spinal Tap? Anybody see that movie?
Yeah.
11.
Do you remember Stonehenge? It was supposed to be 18 feet, and it came in 18 inches. You know, it's not very impressive.
Yeah.
I really like rapid prototyping. I really like people to be able to touch and feel something immediately. You know, it's like when they were doing the Walkman, they took a piece of wood and it was like, it needs to be this size. Sometimes you need to have that sort of tangible sense. And developing software products, what I'd like to do is focus on the user interface and design a beautiful user interface, and then get it in the hands of the users and just iterate quickly. And just you know, doing that sort of thing, we've come up with architectures and systems and products that we never ever would have thought of, and the customers never would have thought of them either. And it's only through that being able to touch and feel and that process that you're able to exploit opportunity. And so the failures I've had have been where we haven't done that, and so the end user, when they actually looked at this, it was like that Stonehenge that was 18 inches tall. It's like, are you kidding? You know, and as an engineer, you feel terrible, but it's because you didn't close that loop fast enough.
Okay, thank you. Anything triggered from this discussion?
I guess I would agree that one of the things that we tend to look at hardware early on as too expensive, takes too long, but in a real sense, a playing between the model-based approach and the hardware verification early, and taking small risk steps maybe is much quicker and much more valuable in terms of finding those faults and those problems that need to be fixed. So I'm a big proponent of this prototyping rapidly and comparing it back to the model and using those two to really find out what reality is.
Before I turn the questions over to the audience, it just occurred to me when I heard John mention a greenfield and brownfield. Is there anyone on the panel here that would like to share what greenfields and brownfields mean to the audience, in case you haven't heard that term?
As an example? Or?
No, just to explain that it's kind of a lingo that sometimes people wouldn't have heard.
Right. You've had something there already. This is how we use it in the auto industry. A manufacturing plant or something, and you're going to retool it rather than build a whole new building. But it also happens in our control systems as well. They start out as, in fact, there was some commentary there, I think, on yours, that those early systems were mechanical systems, and when they came out with the first electrical controlled systems, they were just analogs of the mechanical systems. And that brownfieldness is actually still in control systems 30 years later, because there was that building the system on top of that original system.
Another way that it's often used is a green field. You could think of, I've got a clean sheet of paper to work from. Okay. A brown field is meant, I've got something to start from. But there's all sorts of constraints and other things that I have to help to evolve and extend from.
You may have legacy systems you have to continue to support even as you're building a
Yeah.
new system, for example.
So I'm sorry for not catching that about 2.5 hours ago, in case everyone was wondering. Are there questions? Yes, sir.
So I work with space systems, and there's numerous stories about lack of systems engineering causing extensive failures and so forth. But I was interested in the other side of it, that you could also imagine your response to that to be very rigorously, rigidly specify interfaces. And you're talking about complicated, more complex systems with more and more interfaces. And so my question is, I wanted to know how to tell whether you're doing good, robust systems engineering, or if you're just adding excessive bureaucracy that's going to cost a lot of money and not get you much benefit.
Great. Paul, do you want to start the discussion?
That's an interesting question, and the right question to ask. Einstein once said, a theory should be as simple as possible, but no simpler. Because if it's simpler, it doesn't really work, right? And with all these kind of systems that we're building, for example, SEI is known for processes, and yet you can carry processes to an extreme where it just doesn't matter anymore. You're a process expert, but you're building nothing. Ultimately, we're building things to build a product, to build a functionality, to build something useful. So I think in all these things, you have to figure out, well, you want to do as little of the bureaucratic side of this as possible, but no less. Because if you do if you go past that point where you're doing the too little to make sure the system is going to be secure, safe, do its functionality, then you're going to have a disaster. That's an art. That's not just a science right now. That's where smart people come in with judgment and with experience. And so you see, I think John and some others have mentioned the value of having different views on a program. Even if you have great systems engineers, you need great electrical engineers and great mechanical engineers, right? You need people with all these different views to help balance out the design that you're building. I think that's the most important thing as you go forward on these.
As I think John would critique many of us in military and aerospace for, it's quite often that we get a little too process-centric.
Yes.
And we fall in love with our processes, and we forget that the primary step in any process is, step one, tailor the process to circumstance. If you are dealing with a new, unprecedented system, particularly one that has to be man-rated,
yes,
that's going to push you to one edge of the extreme. If you're working with a highly precedented system, largely a product line scenario where you're varying in a specific area, maybe you're moving from the iPhone 5 to the iPhone 6 and it's not man-rated, you've got a completely different case. And it comes down to the tailorability of those processes, and the only people who can tailor those are the voices of experience.
Yeah, building a shrink-wrapped game software might be different than building a nuclear command and control system.
Yeah.
You might want different processes.
Yeah, and I would also say, in many cases, the overall system's not owned by any one company. So what I talk to a lot of the engineers in my team about is understanding the N+2 system, whatever system we're working on, plus 2 systems above, because it will drive a different behavior. Because say you're building a tree or a blowout preventer, the weight might not be as important to that system in and of itself. When you think that for every pound you put in a blowout preventer, puts a pound in a riser, puts 2 pounds in the ship, you start adding up pretty quickly as you do that. So understanding all of those attributes, and then whether it's a flow, whether it's a loads, whatever it is, passing on across there. So less about interfaces and more about interactions. How does it interact with the N+2 system to understand those attributes? And it's always a fine line between overdoing it and underdoing it. But it's like good art. You know it when you see it.
Yeah.
I mean, if you're writing a report that's never going to be read,
it's probably not important.
that's probably not a good use of your
good
time.
report. Yeah.
If you're holding a design review to get a check mark versus to find defects, you're probably doing the wrong thing. I mean, there's a lot of things you got to ask yourself the why question.
Yeah.
I mean, if I go through a design review and I don't find anything, I'm like, what a colossal waste of time, you know? You need to say, it's good, we want to find problems in our system, we want to find them here and now. But quite often what I've seen is the engineering organization does one thing, and then it goes back and creates a bunch of documents to make it look like it did it in a different way. You know, that's counterproductive.
Yeah.
So, I mean, it doesn't matter to me how the organization works, but come up with a way that's effective, and then have a process that documents what was actually done versus trying to make it look like something it isn't.
I mean, the tailoring is really crucial, and you got to tailor it to the task that you got. And I mean, if you're in the space business, you know you're going to do something a little different for a man-rated system versus a nanosat, right?
Colleagues, any other thoughts? You know, let me kind of summarize what I think are a couple of key themes there. And I'll go back to my space system days. When I was working in the NRO, it was a hell of a lot of fun. But it was preached to me, we've got 10 system behaviors that we care about, and is the reason we might be spending $5 billion over the next 5 years. You know, and those were drilled in my head, absolutely drilled in my head. There was a huge bureaucracy that, given a set of processes that they had actually embraced, and then processes are some of these things that seem to have be organic. They continue to grow. And so there was a designated devil advocate who was empowered to effectively ask the following question: why is doing whatever you're doing on this documentation chain relevant for producing one of those 10 behaviors? And I can tell you, I have seen organizational cultures who are not healthy simply because they will not embrace the devil's advocate that is paid to say why. That kind of bubbles it back to the mission objective and things. And so I would urge you that maybe you need to be one of the devil's advocates, and I understand that that can get pretty uncomfortable at times. But if you do it in a powerful, non-judgmental way, one, you'll show a level of leadership behavior that I don't believe will be missed by people who are interested in your career. And you might be able to do some things that are very important for your organization and its mission.
And even in your own work, that's a good thing to ask yourself.
Yes.
Sometimes challenge yourself. Why am I doing this?
Why?
How is this going to contribute to the mission?
Yeah, have I just slipped into the same rut that I did it yesterday?
Yeah.
I wish that one didn't sound so familiar to me right now. How about other questions? Yes, ma'am.
So I want to go back to designing systems. Ask a question about that. So do you guys have any practical examples of effective ways you've been able to handle this concept down selection problem? So we have the spider web and all these variables that we can change. So when you're considering these concepts for designing your system, what are some means that you've been able to narrow that down? Or specifically, what are some ways you've been able to incorporate the probabilistic aspect in trying to focus on mitigating the risk in that down selection process?
Who would like to take a first thought on that?
I think we've taken a couple of approaches that have worked well. First of all, at least in the areas we're working, if it's a physical system, the first principles approach will never fail you. And as simple as that sounds, I've been involved in many programs that the initial assumptions do not pass the basic fundamentals of thermodynamics or anything else. Then another thing currently in the current era of data is, depending upon what system you have, is evaluating other systems from a big data analytics, as you mentioned. That's one of the things our company does, is looks at terabytes of information coming off of vehicles. We were actually told we're the biggest now D2D data mover for Verizon. because we move all of our data through Verizon. And when you start looking at very big data sets, you start to see trends that you otherwise can't see when you're looking at 2 or 3 points. So those are the 2 areas that have really helped us out stabilize systems and understand systems. If you don't have the large data sets available, perhaps there's ways to generate those separately.
Thank you, Greg. Other thoughts?
Well, modeling sim is a big part of that, obviously. When you're on the government side, you end up receiving all these different designs that contractors bid to you. And so you see the different approaches various companies are taking and designers are taking. Often they're taking an approach based upon their own heritage. You know, what do they think they're good at and what do they think is risky for them? And so you'll see some different approaches that way. Then on the government side, just as you would inside a company with a bunch of designers, you got to start saying, well, what's the most important thing to me? What's the risk with each of these approaches to achieve that which we're trying to get? And I think where sometimes the government has gotten themselves in trouble over the last 25 years is having too many critical things. If you say all these things are critical, then really ultimately none of these things are critical. You got to really have a few that you say are the sacred ones.
Yeah, I would also say more of a generic comment is making sure all assumptions are listed. Because too many times something is an assumption, I think it's true, it might be true, it is true, and that can never be questioned again as you go through the process. So we tend to talk about leap of faith assumptions. The following assumptions were made and they have to be true in order for the outcome to happen. And then how much would it cost and how quickly can we validate or invalidate each one of these assumptions? And we talk about minimum viable products or minimum viable tests that get us to move as quickly as we can and as cheaply as we can to validate or invalidate it. And the other thing around that too is either validating or invalidating is success. Because either way you're a lot smarter and you move forward. It's not pass or fail, it's validate or invalidate and keep moving forward and make the right decisions as you move forward.
Well, and one thing building on that, as programs go on, sometimes you can't validate or invalidate. It's an assumption that you're carrying. So therefore, it's important to lay out up front when you make that assumption, what data point could I see? What behavior would emerge that would tell me that this assumption is now in a questionable state? Because it could come.
Or what sensor would I add
there you go.
in order to measure for that when the system goes out into the field?
One of this isn't exactly your question, but one thing we're finding is that because we're evolving systems more, sometimes people have forgotten what assumptions went into them. Exactly. And they start to extend these, whether it's a sim code or a real live system, they start to extend them into a regime where the assumption no longer applies, and that's a problem.
You know, make it tangible and put it in front of the people who are actually going to use it. Because from an engineer, you look at it from an abstract sense, and it's just numbers. You put it in front of somebody who actually uses it, and they'll say, my gosh, I can't live with that. I can't live with that at all. And it becomes much easier.
And in today's world of increasing computational capacity and ease of modeling and simulation tools, it's much, much easier to put that front end on and stub almost everything else and have it driven by first principle first principle assumptions to start to get that type of feedback and things.
Do you use much hardware in the loop assessments in your job? Where maybe that's not a, so a lot of what we do in the auto industry is have that physical piece of hardware and then write code to actuate that hardware. So we're not working totally in a software regime or a model regime, but we have that hardware injected. Sometimes it's multiple pieces of hardware, and we're actuating actual throttle bodies or fuel injectors, but running it kind of virtually as a model. That's also another way to kind of get your physical systems in there at the same time. So.
I'm actually kind of also interested in the uncertainty quantification part of that. Like, how do you use probabilistic methods to then better quantify the models that you do have of your systems, so you move away from the deterministic models and things like that?
Okay.
That was kind of the second part of the question.
And that's where we use the big data to start looking at those distributions.
And Monte Carlo simulation, where you can simulate lots of cases, with different parameters helps you out in that regard
Yeah,
too.
and then going back to my earlier point too, where there's lots of error in some of the calculations, that's where you would put a sensor when you start doing a hardware in a loop or you start running your testing and those kinds of things to try to bring down your uncertainty around those things.
John, while you're standing up, your colleague to your left, I wanted to ask a question. Do you, sir, want to still ask a question? Well, John's had a chance to ask one, so, yep.
First of all, I want to compliment this panel. I think it's been excellent. I mean, I'm really a big fan of system engineering, and I actually picked the school I went to 30 years and graduated from because they actually offer a BS in system engineering. And I looked at the chart you guys put in that had these attributes on there, and I was like, wow, now I know why. That's me, that's me, that's me. But my question to you, because my frustration is, the first company I worked for, we seemed to have an appreciation of system engineering. It was a very enjoyable job, but in the subsequent years of my career, I've had a real hard time finding places that really value system engineering enough to listen. So I kind of think of the guy, I think of the Fran Boyle filter, pay me now, pay or pay me later.
Yeah.
How do we convince these companies to invest in the infrastructure all the way down to the educational system where people want to do this because they see a good job out there, there's tools out there, there's companies that see that the return on investment as opposed to this short-sighted view where maybe the right system engineering is a lip service thing, but the first budget cut that comes along in the program is gone. Or they move it to the right, which you can't do in system engineering, as you point out. So is that getting any better? Do you agree with it? What can we do about it?
I think that, again, I think unfortunately often catastrophic events create system engineering groups. Certainly in our industry that happens. And I think, Eric, you mentioned the same thing, that you get a catastrophic event, processes are put in place, and often those processes include system-type people to oversee that function going forward. Now, it may dissipate 10 years down the road after all is forgotten, but it's certainly there. And that's unfortunate that it takes a catastrophic event. And the catastrophic event does not have to be injury to people. The catastrophic event could be a financial catastrophic event or a product failure is miserable in the marketplace, and they evaluate why. But in either case, at least in my career, that's been the result. And I agree with you because it's focused on speed, and sometimes the systems people slow it down, or so it's perceived. I believe it's not a slowdown. I believe you're going to slow it down at the end when you don't do it. But at least in the beginning, it's the perception is, well, this is going to add 2 more months to the timeline or 3 more months to the timeline. The reality is it's going to save you 6 months at the end of the program. It's hard for people to see that until the catastrophic event.
Yeah, I heard a comment about doing it right and customizing. That seems to be a real problem because we get labeled as these guys that want tons and tons of requirements documents and the bureaucracy and the time and so forth. And it really is how you practice it.
Are you in the software area or?
No, I'm in aerospace.
Okay.
This is something that I've watched Incosi struggle with over the 24 years of its existence. And it comes down to how do you quantify the cost or the value of an error not encountered? I was taught the law of conservation of systems engineering. For any specific system, there's a fixed amount of systems engineering required to bring it into being. The question is, when do you want to spend that effort? Up front, where maybe you don't ever run into the problem, or at integration and test, where it's really expensive. Now, the single best thing that I've seen come along recently, Paul, came out of your organization, and it's a study that Joe Elm led with NDIA, correct?
Yes.
And it is the, do you know the name of the study off the top of your head?
No, but it's trying to show the cost impact.
Yeah, it's the effectiveness of SE.
And it breaks it into the practices of system engineering as well.
And you can pull it off the SEI website.
For free.
And it is the first study that I think I've seen in 20 plus years that starts to quantify statistically valid the effectiveness of applying these systems engineering techniques and the cost of not doing so across a very large number of programs.
Yeah, but it is a bit of a leap of faith.
Yes.
And you have to have the high-level advocates, you have to have the you know, the stomach to put the time in, put the money in for the first time, and then success breeds success on the other side of it. And you have to find the advocate, train the advocates to understand systems engineering, and move forward from there.
And do you work in industry or government?
Yeah,
Industry.
Defense, aerospace, propulsion.
Yeah, because I mean, I've seen the government go back and forth on this too. The government at times will make the statements that system engineering is important, and at the same time in RFPs they'll cut the cost for that. They'll reduce the cost. They won't even allow the cost for contractors sometimes to do effective system engineering, and this repeatedly bites them. But it doesn't bite them maybe for 3 years or 5 years. Sometimes, yes.
I think another comment, in our industry, the systems engineer is typically called the chief engineer, and they are supposed to oversee the product at a system level to help balance it.
Yeah.
And I think the best chief engineers are systems engineers.
I apologize for making it dialogue, but the organizational chart you guys put up there, this company I started with, it was program manager, chief engineer, chief system engineer.
Yeah.
Yeah,
He had an equal say in the triangle there.
yeah, we tend to divide. The chief engineer focuses on
some do.
components, and then the chief systems engineer focuses on the overall system, is how we split it up.
The place that I love for system engineering, and I know there's others, but the place I always think of is the Jet Propulsion Lab. It does a marvelous job of taking engineers, making them become system engineers to think about the system, and then the best system engineers often become the program managers. So the program manager's like a super system engineer too. So they really have engineering insight, even at the management level when they're doing programs.
The place I started out was TRW out in Redondo.
Yeah.
And Rainbow Bull Ridge
Great place.
broke away from Hughes because they believed in system engineering and Hughes did not. So right
Yeah, I know.
DNA.
And we used to have satellite companies that were run by engineers, but not now.
John, we're going to take your question as the last question in this. And as you're getting up, I'll share one other thing here. There isn't a senior leader that I know that is proud of making a dumb decision. Okay? Now, that isn't that, really hear what I said, that is proud to make a dumb decision. In my career as a systems engineer, I have sworn up and down that I have tried to tell a senior leader that we're going in the wrong direction, and they go in the wrong direction, and they end up seeing the consequences in a couple of years. And at that time, I didn't know how to, in a sophisticated way, go, well, I told you so. So I would unsophisticatedly tell them, I told you so. Thankfully, I always had people who were mentors and not willing to squish me when I didn't know how to say something properly. But the most powerful thing that a senior leader told me at that point was, well, if you knew that, why in the world didn't you get to the point and frame it where I could understand what you meant? Now, that was a long story to simply go, our communication skills are paramount in the effectiveness of our leadership. Our systems thinking tees us up to be able to see these things. And it's not easy for us, but always try to remember that story. And that communication skill, chosen correctly, can help nurture that advocate that Eric was talking about. John, one last question.
Thank you all very much. I just want to also compliment the entire panel. I think that was extremely illuminating and insightful to hear all of the perspectives on how do we solve our problems. And I know we have a very short time. By the way, it's incredible that we went through 3 hours and here we are. Hopefully, there's just a little time to maybe address a couple of questions, or a couple of points. Let me not leave you guys without, we talked earlier about the dreaded R word, risk, and Eric was gracious in explaining how they've overcome the law of risk issues, although it was somebody else's design. We understand. And I think there have been many anecdotes made about how system engineering can generally, left to its own devices and capabilities and tools, overcome probably most of the challenges that are in front of them. I think there's no doubt. And we salient example of that, 45, 50 years ago was the Apollo program. I can't believe that, the golden age of system engineering, that was Apollo, probably isn't evident today as it was then. But certainly that shows that human beings allowed to, free to explore and assess and manage their endeavors, will probably find the right solutions for the problem. However, we also heard now that there are, the other dreaded R word I want to bring up is, Greg began to introduce it, is the regulatory, or specifically the regulated boards. John, you mentioned no matter how high up you are, there's always somebody above you. Sure enough, there's always a government or somebody who is looking over your shoulder. And I often find in my 40-some years of engineering system engineering, that I've been in the middle of like a Dilbert cartoon. Dilbert walks into his boss's office and says, boss, I got a great idea for saving. We can save $1 million. But it only requires about a $10,000 investment. Boss says, let me see that. So he said, well, you obviously overlooked the fact that the $10,000 is going to come from my department. However, most of the benefit will accrue, across the company, not to me. Well, yes, Dilbert said, but I think, the boss said it's not feasible. Dilbert said, I think the shareholders might disagree with you. And he says, boss said, yes, that's why we don't invite them to our meetings. And that is a scenario that's played out very often. You guys have been on in several places. So my question is, and John, quote you, to see if you can reflect on this for a moment. You have stated that in Propulsion's mission, one of our missions, is to measure our success by our ability to influence the key decisions. I think you're making that point now. And yet, you know that there's so many episodes where, Paul, you mentioned that, system engineer had the right solution, but, management overruled it. That was the case, by the way, in Columbia. The Columbia disaster could have been avoided, and it was recommended that they aim a telescope at the underbelly to see what they did. However, management didn't want to compromise the mission because it was what could be scheduled, Columbia scheduled. So we didn't do that. That critical stuff. Overruled. So the question is, and I'm going to come back to Greg for a second. You showed the exponentially growing curve on the CAFE standard fuel requirements that's in front of us. And at the same time, we also have exponentially increasing regulatory curve that will keep coming at the design process. At what point are we going to be seeing a requirement for making smaller humans that will fit into the smaller cars? That's bound to happen too. And so seriously, if we look at the situation of how do we avoid these problems, is it the failure of system engineering when we can't convince management, or is it the management failure to understand the essential problem? And how do we overcome that?
Okay, thank you, John. And I guess you focused the question initially on me. Here's what I can tell you in my career. I spent too many years, and I'm going to make this real personal in the way I use these words. I spent too many years being arrogant and thinking that it was somebody else's job to understand me. Okay? Those were extraordinarily frustrating years because the fact of the matter is, more times than not, I saw a system interrelated issue or parts related issue that had huge consequences. At the same time that I spent so many years insisting that it was their responsibility to comprehend my perfectly good thinking, I also ended up assuming, or I took the lack of their understanding personally. That gave me a long set of years in my career where I was able to really brew on just how unjust I was being treated. My career and my impact on my organization changed as soon as I took the ownership on my side. And I can tell you it was painful because what I really found was that there was only a small group of people, kind of like my tribe, that would get whatever I was observing like that. And they'd go, wow, right? Except it was a microcosm. And when I realized I was actually talking to other tribes, I started learning. I purposefully took an intense interest in ownership that goes, if you didn't hear it that way, instead of trying it again 20 more times, I was going to learn how to talk in your language, in your value system, in your perspective. Now, right now it's a continuously learning process for me. It took only about a year for my serious ownership to start to see little differences. Not big differences yet, but little differences enough where I could keep sustaining myself. What other thoughts or reactions does the panel have?
I'd like to address that one because it comes down again to the human element, I think. That person you're trying to influence has a perspective, he has a value system of what he thinks is important. And I think it's incumbent upon us to always be professional in our approach to them, always be proactive, always looking for another way to say the same thing over again, and always be persistent, always going back again and again to get our point across. I think if we really listen in those encounters, we'll get a true idea of where that person is and be able to better frame what we're trying to say.
Yeah.
And I think that's a big part of system engineering is understanding perspectives of other people that you're trying to integrate, but also the stakeholders you're trying to manage.
I think the earlier you learn this in your career, the better it is for you, actually. And if someone else who obviously has been reasonably successful in their career doesn't see the same as you, it might be good to try to understand, well, why do they think differently? Maybe they've thought of something or one angle that I have not completely thought of. Maybe there's another constraint that I don't know is in the system that I have to worry about. So it can be a real learning experience. As you found out, you can do this, So.
And while we focus this on management, I mean, the reality is in the diversity of people that we have to deal with, from customers all the way through to specialists, the same issue comes up, and it's absolutely critical. If there's one book I would recommend, it's Pink's latest, To Sell is Human, which points out that if you're in the information age, most of what you're doing is actually selling. You're selling your comprehension of an idea and therefore whether or not you have answers to it. If you can't do that, the value of your idea is minimized, whether it's to management or to that leaf level specialist who perhaps is seeing something that you're missing.
Anthropology is important. It's cultural.
What, John?
Anthropology is important. It's cultural. I was in one organization for about 10 years, and we built a culture of, quality. It took 10 years to build that culture, but within that culture, you would have no issues because that's the way the culture ran. Moving into another culture that was a blame culture, right? And it was a culture of somebody's going to go under the bus, and you don't want it to be you, and that's the game you play, and you can't just will that culture to change. It takes years. Time. It takes time from the top, and it takes years. It could change. Could take changing the entire leadership team. But you have to be aware of the culture you're in, and you have to be aware of the limitations of what you can and cannot do, and what you're willing to do. Maybe you could move the organization a little bit. Maybe that's enough for you. Maybe that's not enough for you. Find a place where you fit in, and that's the right fit for you in terms of your culture and your sense of integrity.
Panel, any other comments? Yes.
No.
Okay. I guess I would wind this down by a quote that Covey has been attributed to him. He said, are you a person who spends most of your time listening to respond? Or are you a person who spends your time listening to learn? The other point of view. I can tell you that when I was in my early career mode, it was the first. I was just listening so that I could show them exactly why all of those points were irrelevant, and because I had the relevant one, right? When I started listening to learn, I expanded my skill of understanding that I actually was looking in a more myopic way at a broader systems problem, which was a little embarrassing to me because I was supposed to be a systems guy, you know. And secondly, I started to learn their language and their values so that I could translate back to them. So that would be what I would share. I want to thank my panel members for an extraordinary set of things that they've shared in this meeting. I want to thank this audience and its engagement. And I believe we ought to declare success. It's a little bit past 6.